Now, continuing the delta epsilon definition of the limit, I want to repeat many times that the whole point of the delta epsilon definition is to show that it's not. A lot of times you can't figure out what the function is at a specific point because you're dividing with 0 or some such other similar reason. Okay, it's not defined. You can't define it. However, you notice an interesting property is all the numbers right next to your interested number. That is, you have a number that you're interested in, right? That's a, and you have a function that sends a to somewhere else. And then, but the problem is the function f is not defined at a for obvious reasons. Like you have to divide by 0 at a for some reason. So it can't do that. However, you notice sometimes you notice a very interesting quality. That is, if you look at a very small neighborhood of a, like in here, okay, I'll draw a very small neighborhood. So small, we call it the delta neighborhood. If you look at a small enough neighborhood, then everything inside A, which are defined, all land within a very... Sorry, I forgot to lock up the screen. Now, as I was saying, when you have a function that goes from A to L in area around A but not A because it's not defined, you notice an interesting quality of this function. That is, they all seem to be, all the stuff that's next to A, which is defined, all land right next to something called L, very close to it. In fact, it's within a small distance, a small error tolerance called epsilon of L. If that is the case, if everything in the neighborhood lands that way, then you can say that the limit of the function at A is L, because you can't say what the value is, so you just go to the limit. In other words, you're not allowed to calculate directly the value of the function, so you are looking at the neighbors. See, the neighbors are now represent the guy, okay? So the neighbor's value will be good enough, and you are only looking at a very small number of neighbors, okay? Very small as you can make it. But it's still okay because the function is only not defined at A. It's defined at all the neighbors that's right next to it. So, having said that, let's look at another example. This is example, what is this? Oh, 2.41. So, example 2.41, which is on page 199. 199. All right. So and then we prove this another simple problem, that is prove that limit of x approach 2 of x squared equals to 4. Now we have already done that a couple of sections ago, right? As x approach 2, x is defined at 2, so its value is just 4. X 2 squared is 4. But we're going to prove it because to demonstrate how the epsilon delta definition of the limit works. So let's see how that goes. Okay. So you need by the definition, which you must read that short definition again and again, a part at a time, until you understand it. That will be the homework today. Okay, and that might take a while because that definition is cryptic, but you need to get used to it because you're getting into advanced math now, and you have to start taking the hard punches. So anyway, so there's this, and so how do you do that? Well, the definition says you have to prove that the function is within epsilon. So what do we want? So you're given epsilon, right? So you're supposed to prove that x squared minus 4 has to be less than epsilon if x is... You have to prove that the function x squared is within epsilon of 4 if x is within epsilon of 2, within delta of 2. So how are we gonna, so we need to find some kind of delta in terms of epsilon is what we're trying to do. So how are we gonna do that? So all right, so you factor this. You always factor something. If you don't know what to do, you factor. You know, it's like Dory says, we're fish. When we don't know what to do, we swim. Now we are math students, so if you don't know what to do, you factor. So let's factor this thing. And this is, again, difference of squares. A squared minus b squared is a minus b times a plus b. So you do that. X minus 4, x plus 4, and so on. And you want this thing to be less than epsilon. Yeah, sorry, I already messed up. Is squared. Okay, so you need a, this is 2. 2 times 2 is 4. All right. Let's get rid of that. Okay, that's better. Okay, so 2 and 2. Now at this point, I'm gonna pull a trick to because I'm aiming for this. X is approaching 2, so I need to know what x minus 2 has to be. Now, being that x is approaching to 2, I can argue that this x is almost 2, so this number is almost 4, right? It's 4 or close to it. So therefore, I can argue that, so I replace this number. It's reasonable to say that x minus 2, I'll put x as 0, okay, times 2. This particular number expression is going to be less than this, right? X minus 2, x plus 2, less than epsilon. Why? Why is that? Because x is almost 2. If it's almost 2 and everything's in absolute value, so you don't care about negatives and stuff, so then this thing, when x is close to 2, has to be bigger than that, right? Yeah, I mean, because x is almost 2, so it's always bigger than this thing. All right, now having said that, then I forget this thing for a second, and we focus on this. And then we will say, then x minus 2 times 2 is less than epsilon. We're still trying to find something here. Okay, where is x minus 2 going to be? We need to find the delta such that make this happen. So then let's divide both sides by 2, and then x minus 2 is less than epsilon over 2, which we will set delta to be this value. Okay, because if delta is equal to epsilon over 2, then all these inequalities work backwards, and x squared will be within epsilon of 4. And then, so that is your answer, okay? We'll set delta equal to epsilon over 2. So by the definition, if somebody gives you an epsilon, a very small number, all right, then you can find the delta. You will set delta as half of that small number, so it's even smaller. And if you do that, then everything that's close to 2 will end up being within 4 of epsilon. That is, for example, like a would be 2 here, okay? As long as your delta is your epsilon's here, and then everything within, as long as your x is within the delta of a, which is 2, then the whole thing will work out. And that is my demonstration of the delta epsilon proof for this particular example. Now, the delta epsilon proof, you have to pull some tricks, and the goal is only to find a small delta. It doesn't have to be exact, as long as it's small. For example, you say, well, this condition works, being that it's an inequality. This condition works if delta is equal to epsilon over 2. What if delta equals to, say, even smaller, epsilon over, say, 4? Yeah, that works too, right? Because the definition says you need to find a delta small enough so that every x will end up being within epsilon. Yeah, if everything within epsilon over 2 fits, then if you restrict the area, then everything within, if it delta is smaller, then it for sure fit. So it doesn't really matter what you find as long as it's something small and it's something that works for every epsilon that is handed to you. So the epsilon is given to you and your job is to find the delta such that everything around your point of interest will land within the epsilon error tolerance. And there can be no exceptions. Oh, in this case, there is none. See? And at this point, you might ask me, what is the book saying? Because the book gives you a big, long solution that doesn't look like what I say at all. Which is okay, I guess. But I just like the easy. This is the easy way, and I'll stick with the easy way. All right. So the point is that you need to find a small region with delta where all the numbers will land within epsilon. So that will work. Delta equals to 2 will work. And in fact, yeah, anything smaller than that will work too. Anyway, so the delta epsilon proof is you don't have to come up with an exact value like what is 2 and 2. The delta epsilon proof is talking about the neighborhood. What are the neighbors doing? And it doesn't have to be all the neighbors in town. It's just the neighbors right close to it. All the neighbors right close in a very small area, as small as required, such that every neighbor does the same thing. They all land within the error tolerance. Okay, that is, they all hit the target. That is all the delta epsilon definition is going to say. Now, having said that, I'm not gonna cover. We're gonna skip through the rest of the section about delta epsilon rules. The reason is because the delta epsilon definition is a very sound, logically solid foundation for limits, which is required for calculus. But at the same time, being that it's just the foundation, we are probably not going to use it again. Okay. And when we study differentiation and integration and all that, this is just what we base on, but we're not actually going to look at it. Because this is just how this is founded. So as a result, well, some professors don't even mention the delta epsilon thing because it's not used again. Why are we talking about it? For me, I feel that we should talk about it, but at the same time, let's not get off the rabbit trail and go in detail because you can just keep going and waste time because I want to get through calculus. So my decision is that after we finish calculus 1, we will go back here as a reward and cover some of the stuff that I skipped over because it's very interesting stuff, but it's sort of off topic for us. All you need to know at this point is that there's a rigorous calculus proof, definition, which is the delta epsilon definition. So for homework of this section, I just want you to spend up to an hour reading that delta epsilon definition. If after a reasonable amount of time and you still have trouble understanding all of it, then I recommend, well, first, if you understand it, that's great. But if you do have trouble understanding it, and some people do because it's a very unusual, okay? It's something you've never seen before in math. So if you do have trouble understanding it, then I recommend that you memorize it. It's just 3 lines or something and very short, right? I want you to memorize it and then move on. And of course, I did 2 examples, I believe, in this section. Redo the examples I did with the way I did it and see if this makes sense to you. But having said that, let's move on. We need to get to differentiation or we're never going to get through calculus.